So next we are going to show various different forms of periodic table. I'm sure you all have seen one periodic table, that is the modern version, the most accurate one. I'm going to show you the other different versions. Just out of curiosity, I'm showing these things. I hope you guys will enjoy these things. So let's see what are the other types of periodic table present there. The first we are going to show Corbino's right state periodic table, which came in 1928. So this is the Corbino's right state periodic table. It was published in the same year as Janet's left state formulation. Corbino saw if blocks shifted by corresponding value of quantum number L, then the rows represent electronic shells. So you can see, so there S means L is equal to 0, then P block comes, means L is equal to 1, then D and F. So in like that, from S, P, D, F, they have, Corbino has arranged these elements. Now next, this one is the racetrack periodic table. Chemist and sci-fi author John Clark created this racetrack periodic table in 1933. Now you can see here we have hydrogen, then helium, then lithium, beryllium, boron, carbon, nitrogen, oxygen. Again we have fluorine here, then neon. Like that it goes round and round, round and round. That's why it is called racetrack periodic table, like a racetrack, Formula 1. Next we have Akimov system. So Akimov system took the form of a cross section of pyramid, and he based his system on the principle that the lengths of the periods and analogies in properties between the elements of these periods must be clearly demonstrated. So you can see here we have hydrogen, and this side we have helium. Then lithium comes this side, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. And you can see this one is going like this: hydrogen, then lithium and sodium, then here potassium and rubidium, and then here cesium. So this one is going like a cross-sectional pyramid. Next one is the spiral periodic table. So one of the Bentley's publications in chemistry was a model of an extended periodic table, sometimes referred to as periodic snail. So this is referred as periodic snail. So this is this extended version of this racetrack periodic table. You can see hydrogen here, then helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, and it goes like this, and after that it comes here in the D block elements, and again it goes here, the S and P block elements, and after this D block elements, you can see it will go to the F block elements, and these F block elements are here, lanthanides and actinides. This is also referred as periodic snail. Next one is the curl-driven periodic table. So it was created by James Franklin Hyde in 1975. So this is also another extended version of that racetrack periodic table, and you can see it starts from here and all the way it goes there, and here we have the D block elements this side, and after that going here these F block elements comes this side. So these are the different versions of a racetrack periodic table. Next we have Mayan periodic table. So the Mayan periodic table of elements named for its similarity to the ancient Mesoamerican calendar. It shows electron shells as concentric circles. Each row in the tabular form is shown as a ring. So you can see here we have hydrogen, then helium, and then lithium, beryllium as a ring. And again, if you take from sodium to argon as another ring, you can see another ring. So it goes as a ring and ring. Again, you have to start from potassium, and you will get another ring, till potassium to krypton, and again from rubidium to xenon, you will get another ring like this. It goes like ring wise. Next, we have the Adoma periodic table, so which came in 2006. So it was proposed by Worley Shimmerman. It is based on the Janet or left state periodic table. It consists of 4 blocks S, P, D, and F corresponding to quantum numbers L is equal to 0, 1, 2, and 3. So if you see, you can see the S block elements are here. So you have to start from here. You can see hydrogen and helium. Then you have to come to the P block elements. So it will be like hydrogen, helium, lithium, beryllium. Then you will come here boron, carbon, nitrogen, oxygen, fluorine, neon. Similarly, when you have S, P, and D, so first you will come here sodium, magnesium. Then you will come here aluminum, silicon, phosphorus, sulfur, chlorine, argon, and then you will come here for the D block element, scandium, titanium, all these things. So first you have to fill this S block, then you will fill this P block, then you will fill this D block, and after that you will go here and you will fill this F block. So like that, it is that consisted of 4 blocks. Next we have this nucleosynthesis periodic. So a version of the periodic table indicating the origins, including Big Bang nucleosynthesis of the elements. All elements above 103 are also man-made and are not included. So this periodic table tells how these atoms got originated. So you can see this hydrogen and helium mostly from Big Bang fusion. So if you see this color, that tells it is coming from Big Bang fusion. And this one is cosmic ray fission. And this color, if you see this strontium, yttrium, these are having most greenish. They are coming from dying low mass stars. Again, this color, if you see, it is coming from merging neutron stars. So all these different colors, or this ratio of the colors, they say how much percentage of this atom is coming from merging neutrons and how much percentage of this atom is coming from dying low mass stars. So this is a different type of periodic table. Now next we have Wies's tetrahedron. So Dmitry Wies shows how it is possible to go from the Janet periodic table formulation to a tetrahedral formulation. So this is just another type of block periodic table, but he arranged it as a tetrahedron. So you can see these are the S block elements, then we have the P block, then we have D block here, and at the end we have F block. So all these blocks can be arranged as a tetrahedron. So where we have S blocks on the top, then the bottom layer comes the P block, after that the layer comes the D block, and the last layer comes as a F block. Next, another interesting one is the Pizza-Lunker's circular periodic table. So you can see this periodic table is made like a pizza. So this one is hydrogen and helium, and then we have lithium, beryllium here, and boron, carbon, nitrogen, oxygen, fluorine, neon this side. So first you fill the S blocks this way, and then you fill the P blocks like this way, and then you fill the D blocks like this way, from here to here, here to here. But inside the D block, we have F block elements. So that's why we have to fill the F blocks this way. Next one is the Adama periodic table glass cube. So you can see the periodic table has been fitted inside this glass cube. So Worldly Schimmermann of the Adama periodic table and the Adama tetrahedron has now used these ideas to produce a beautiful glass cube. Next one is Janet Rajuni. So this is also another kind of periodic table where this is also kind of that block periodic table, and you have S blocks here, then we have P blocks here, then we have D blocks, and then we have F blocks. Next one is the Adama periodic table and normal. So the Adama from here resembles the normal distribution or bell curve. So you can see like this bell curve, bell shape. So how to fill? So you have to fill it here, hydrogen and helium, then lithium, beryllium. Then you have to go here for the P block, boron, carbon, nitrogen, oxygen, fluorine, neon. Again after, so you have to fill this S block here, then you have to fill the P block. After that you will fill the D block like this, and then you will fill the F block like this. And you will stack on top of each other. Next one is Naoma's Boyobu Janet periodic table. So a Japanese school teacher, I'll show him, and he has made a lot of periodic tables. I'll show some more later. So he designed this Janet form of periodic table in the traditional Japanese Boyobu style. So this is the Japanese Boyobu style, and you can see that S block and P block elements are here, this side, and then we have D block elements, then we have F block elements. So this one is called Boyobu style. Next we have clock face periodic table. So this is Professor Martin Polyakov, is a very famous professor as well as YouTuber. So he had made this clock face periodic table. So in 2014, Professor Martin Polyakov showed us a working periodic table clock. The designer of the clock is Nagayasu Nawa, a Japanese school teacher. So here you start from here, hydrogen, helium, lithium, and you will all the way you go from one end to other end. And then you get the F block elements, and you will go again like this. So it's a kind of clock periodic table. Next one is the Sensu or fan periodic table. So Nagayasu Nawa, as I was mentioning, that Japanese school teacher, he made various kinds of periodic tables, and one of them are this Sensu or fan periodic table. You can see it starts from here, hydrogen, helium, lithium, beryllium, then it goes all the way here, and after that it goes here for the D block. It starts here and it goes all the way, and then you start the F blocks from here and you go all the way. So it's kind of fan periodic table. Next one is the clock prism periodic table, and this one is the Braille version. So for those who cannot see, they can touch this and they can feel the periodic elements. That's why it's a Braille version of clock prism periodic table. So Nagayasu Nama, that Japanese school teacher, he has made a lot of periodic tables, and he has a homepage where he showed all his inventions and innovation regarding these periodic tables. You can go and visit. You can type Nagayasu Nama, you will find his homepage, and go and check all these periodic tables. He is the man, Nagayasu Nama. Next one is Moran's periodic spiral. So Jeff Moran has updated his 1999 periodic spiral, and it looks like this. Now how did it do it? You see hydrogen is here, then helium, then lithium. So hydrogen, helium, lithium, beryllium. Then you have to find the boron, and you can see boron is here. Boron, carbon, nitrogen, oxygen, fluorine. Again, neon is here. So this is kind of complicated, but if you really see it carefully, you can find that it's a spiral kind of thing. So you have to start from here, or you can see this line. Start from here and go like this, this, and again you come here and go like this, then you will get neon, then again come here, the sodium, magnesium, and then you come all the way down, go like this, and you will get aluminium, silicon, phosphorus, sulfur, chlorine, then you go to argon, and then again you come to potassium, calcium. So it is kind of spiral. It's a very different kind of arrangement. You just take a proper look, and you can understand this one. Next we have Stewart's periodic table. So P.J. Stewart has mapped a periodic table onto a sphere. So on the surface of the sphere, he mapped this periodic table as a blockwise SPDF block, and then it looks something like this. If you see, these one are the S block elements. Here we have P block elements. On the side of that, we will have D block elements, and then we will have F block elements. Next, we have another kind of periodic table, that is Simpson's 4-dimensional version of the Adama periodic table. So this is also kind of same block kind of thing. But how they are doing? You can see these S block elements are here, and then in this first layer is the S block elements, and then we have p block elements on the back of this s block layer. Then we have d block elements back of this p block layers, and then we have f block elements back of the d block layer. This is kind of 4D version. Next one is Nava's 3D octagonal pillar. So this is kind of same thing. You can see hydrogen, helium, the lithium, beryllium, boron. So just like a pillar, he just so kind of go around this pillar, lithium, beryllium, boron, then go in the back. You can see the back, carbon, nitrogen, oxygen, fluorine. Again, he will go here. So this is kind of 3D octagonal pillar means on top of a pillar, you are writing these elements in a swirl motion. Next one is Nava's VET periodic table and hourglass. So this is a very interesting periodic table, and I will show you in the next slide how the electronic filling is happening there. So this is the same thing we see. This is also blockwise, S block elements, and then P block elements, and then D block elements, and then F block elements. But I will show you how this electron filling is happening. He has shown in this hourglass periodic table. So watch it out carefully. So hydrogen, helium. I will go back. I will start again. You see the electron filling. So for hydrogen, there is half field, then helium, two field, 1s2, then 2s1, 2s2, then 2p1, 2p2, 2p3, then 2p4, 2p5, 2p6. So all these elements, you can see the filling, how this is happening. Then again 3s, 3p3, 3p4, 3p5, 3p6. Just see the filling of electrons here. You can see all these electrons, how it is filling one by one. And now we are filling this F, 4F, now 5D. So you can go back and you can try to realize how this electron filling is happening. You can just tap in the video and go back and see it again. So this, they have also at the end showed how in the future that other elements are possible to come. Now next one, we have the periodic table of element scarcity. So in this table, they have mapped what is the abundance of the elements. So for example, if you see this green one, this means that is plentiful supply, that has plentiful supply. Hydrogen, sodium, potassium, calcium, the abundance is more in nature. Now if you see the yellow ones, that has limited availability, future risk to supply. If you see vanadium, scandium, manganese, nickel, copper, these are the yellow ones. These white ones are the synthetic ones. There are some more, and you can see this technetium that is in white color. This gray one, that from conflict minerals, you can see here, tantalum, gold. And this mobile sign, these are the elements that are used in the smartphones. So you can see gold, tantalum, tungsten, tin, these are used in the mobiles, as well as these ones, F block elements, D block elements, some of the D block elements also you can see, cobalt, nickel, copper, gallium, all these things. Even these P block elements, carbon, silicon, oxygen, these are used in the mobile phones. Now let's come to the availability. And if you see this orange color, that means rising threat from increased use. So if you use more and more, so that will become threat to human being. So you can see these ones, europium, osmium, ruthenium, palladium, platinum. And this red one is that serious threat in the next 100 years. So these red ones are very, the scarcity is more. So if you take strontium, yttrium, these are very less in amount, and it can be finished within next 100 years if you use more and more, right? Now next we have Stewart's quantahedron formulation. So this is also another kind of 4D periodic table, and you can see these S blocks, P blocks, D blocks, and F blocks. These are arranged as a quantahedron. This is kind of also 4D arrangement, same as that. Now next is the periodic table of chemical bonds. So this one we owe to mathematicians at the Max Planck Institute, who investigated almost 5,000 substances containing two elements in different proportions. Each circle in this hypergraph represents the bonding an element establishes with an organic residue. The bonds are then ordered by their polarizability, where more polarized bonds place the element higher in the graph. Here, two elements can be compared either through a direct arrow. Example, the bonds of hydrogen, for example, are more polarized than those of boron. So you can see these are the bonds. These are the bonding between the hydrogens, and this hydrogen is on top. That means it is more polarizable, and then or by the chain of arrows between them. For example, the oxygen bonds are more polarized than those of bromine. So if you see bromine, bromine is here, and oxygen, so oxygen is here. So these oxygen containing bonds are more polarized. So either you can compare the position of the atoms not linked to each other, or you can see the atoms, those are linked to each other through an arrow. That means they make elements together, so binary elements. Whatever is on top, that has higher polarizability. This is also a very interesting way to show the elements. But yeah, this took a lot of efforts to analyze all those 5,000 substances. Next, we have rainbow periodic table in ATOMA. And so this is kind of same as, just let me see, yeah, S block elements are on top, then P block element, then we have D block element, and in the last layer we have F block element. Next one is this NAWA's rainbow periodic table, and you can see, so a lot of information is given in this rainbow periodic table. That means he has done a lot of color coding, and he has said what is the meaning of these color codings. You can see this K, L, M, N, O, P, Q, R shells. So where this last electron is going, accordingly, these color codings will be done. For example, you can see in hydrogen, the last electron is going to the 1s, that means K shell. So that's why red in color. The helium, it is going to 1s2, K shell. So that is also red in color. Then we have orange in color, this lithium, beryllium, boron, carbon, all these are orange in color. So these are the, if you see the symbol, you can see this much of information is given here. And also the type of the elements also given here. So have a careful look and try to understand what are the informations given here. Next one is the NAWA's multi-periodic table that came in 2021. So this is actually a complete circle. I tried to show it in two parts so that it is properly visible to you, but it will be actually complete circle. If you go and see his website, you can see it is a complete circle. And this arrangement is also kind of a clock. So you start from here, hydrogen, helium, lithium, beryllium, boron, carbon, and you go all the way to this one, and then you come to the F block elements, and again you come this way, and then after this you have to come this circle. Yeah. So this is a complete one full circle. So I have cut it down just to show it in better way. And yeah, you can see these color codings as well. So when it is found at of discovery, according to that, these are the color codes, and these are also time. I'll zoom it in. You can see, oh shit. I'll zoom it in, and you can see according to the timing when it was found, when it was discovered, he has color coded all the elements. And here in this word, in this part, he has color coded all the elements according to the abundance in Earth's upper continental crust, Earth crust. So this one and this one are also different kind of periodic tables that people have come up with. And this one is kind of looks like a mobile game, right? This one is also another 3D periodic table. This one is also kind of a periodic table.
Hey genius, I hope you liked the video and the concepts are clear. So if you want to know more and if you want to learn more, you can go and check the periodic table and periodic trends folder. I have already uploaded 7 lectures on this topic. Please go and watch all those 7 lectures. I hope it will be very useful for you. And if you think these videos are knowledgeable, please share it with your friends and don't forget to subscribe. Okay? Thank you. Bye bye.